Hello, everyone. I'm Courtney Chambers, your webinar host from the Engineer Research and Development Center. I'm glad you could join me for a start of the summer webinar series brought to you by the Corps of Engineers Invasive Species Leadership Team, partnered with the University of Florida Institute for Food and Agricultural Sciences, which you'll hear me abbreviate as IFAS, the acronym. We've identified 7 invasive species topics with University of Florida IFAS and others from the Corps. You'll hear from some district partners as well as others from the Environmental Laboratory. And those topics are going to be presented weekly on Wednesdays at 1 o'clock Central Time, like we're gathered here today. And I've prepared the list of those topics in a flyer, and I'll share that with you at the end of today's meeting, and then also try to circulate that through email. And we'll continue to do so. But I just want you to be aware that we have an increase in frequency through the summer here of lots of interesting invasive species topics. So to start off our series, we're going to hear about 2 topics today. First, an overview of aquatic plant management research program at the University of Florida IFAS, and then a new aquatic herbicide treatment for Hydrilla and efficacy and an operational treatment in Florida. Okay, at this time, I'd like to introduce our speakers today. And then we'll also be hearing from Dr. James Leary, who is an assistant professor for the Center of Aquatic and Invasive Plants, also at the Institute of Food and Agricultural Sciences at University of Florida. He was born and raised in Michigan, where he earned his bachelor's in horticulture and chemistry. And then he relocated to Hawaii in '97 and earned his master's and PhD there in horticulture and molecular ecology. He served the last decade stationed on the beautiful island of Maui as an associate professor for the University of Hawaii in invasive plant species management. He has over 20 years of experience in tropical weed management, and now he starts a new chapter in aquatic plant management, continuing his mission to extend knowledge and technology contributing to efficient and effective invasive plant species management in natural and managed landscapes. So I want to thank you both of you guys again for your willingness to share your work. All right. Well, Dr. Leary, let's go ahead and proceed to your presentation. So I'll make you the presenter.
Okay.
We can go ahead.
Very good. Thank you, Courtney. Okay, thank you. Okay, can you guys all see my screen?
We do. It looks good.
Okay, great. Thank you very much. Courtney, thank you for arranging this opportunity. Dr. Sperry, excellent presentation. I know I'm just I'm just next door to you, but it's fascinating to see how far you've come in a short period of time. Really interesting stuff. I'm going to switch gears a little bit and focus in on one particular project that I've had the opportunity to participate in. I also am new faculty with University of Florida, as described, and I came in right as a new herbicide product was being registered for Florida, Procellacor SC, which is a product of CPRO. And so I had the good fortune of teaming up with new members at the university and industry partners as well. And so I'll be presenting on later stage research for deployment of this new herbicide in field applications. And so we'll be talking about fluorpyroxafen benzoyl suppressing hydrilla in Fish Lake, which is a small eutrophic lake in Florida. Really don't want to focus on the uniqueness of Florida lakes. I know that we have a broad audience with different lake types, but it does lend itself to challenges that are also unique to Florida. So without further ado, I'd also like to acknowledge colleagues who prepared this research and developed it and cultivated the story that's being told today, including Dr. Sperry, who just presented, Jay Farrell, our director at the center, Dean Jones, who was our biologist during this project. He was really the lead on a lot of the data collection and experimental design, including Mark Heilman, who's also online and listening in, and Kelly Gladding, both with CPRO at the time. Moving on. So let's talk a little bit about hydrilla management in Florida to set the stage. It was introduced in Florida in the 1950s. Classic invasive species biology, where that species is introduced as an ornamental in the aquatic trade. It gets released into the natural environment. It's a favorable, suitable habitat for it to survive and naturalize. Goes undetected for up to several decades. Then in the 70s and 80s, all of a sudden we realize we have a problem and the cat's out of the bag, or the horse is out of the barn, whichever you prefer. This is where action was taken at the state and federal levels, identifying solutions to a really large problem where they had identified fluoridone as a whole lake treatment to be highly effective at very low doses and selective in protecting other non-target species, namely a lot of the native aquatic species that Florida lakes maintain. Of course, within a decade of use pattern, aggressive use pattern, resistance was identified in the mid-90s and forced our partners, researchers and practitioners to identify alternatives. The one alternative that stood out among the others was the use of endothol, which is highly effective, but it resulted in increased use rates and also was not practical for whole lake treatments like fluoridone, but instead became partial treatments. Regardless, highly effective application and the current standard still today in Florida. However, because it is one of the few options, it is a practice that's over relied on, and it also is vulnerable to resistance development by Hydrilla. And so part of our research agenda over the last decade and a half has been to identify new herbicides to diversify our portfolio so that we can mix and match different active ingredients and different modes of action to mitigate against the development of resistance, hence leading to the development of fluorpyroxafen benzyl as an alternative and in the toolbox for controlling Hydrilla. This is an auxin herbicide. It's considered a reduced risk. It's classified as reduced risk because of its low use rates. Its fate in water is that its decay half-life is approximately 1 to 2 days and a pH over 9, but it increases with lower pH. But most lakes in Florida are somewhere between 7 and 10. So not the half-life in Florida lakes are low. The primary mode of degradation is photolysis when in water. Some of the other chemical or physical features of it has low solubility. It's insoluble at 15 parts per billion, which is within the range of the treatment application. It has high KOC and KOW values, meaning it's lipophilic. It adheres to organic materials and other components, but it also has very low use rates. The labeled rate is between 19 and 48 parts per billion, which is, according to label, what would be considered 2 to 5 PDUs per acre foot. Again, kind of going back to the photolysis, the rapid rate of photolysis experienced with fluorpyroxafen benzyl deesterifies into the parent acid material through hydrolysis. So we'll be talking a lot about fluorpyroxafen benzyl and fluorpyroxafen, the acid form, otherwise known as, in my case for this story, FPB and FPA. Prior to doing any kind of field research, you need to understand how the chemistry works, and this is in aquatics. This is where musicosm research really pays dividends to understand its efficacy and environmental fate and toxicology. These are major contributors towards getting a new herbicide registered. It's a really critical function of what we do. And so early in the last decade, there's been a lot of work by late great Mike Netherland, Rob Richardson, and his graduate student Jens Dietz, developing use patterns or understanding the efficacy on Hydrilla, our understanding of the sensitivities to water milfoil, and then also identifying tolerances such as with potamogeton, typha, and scirpus, valsinaria. A lot of the aquatic grass species having tolerance, lending itself to the opportunities for selective treatments for controlling our noxious target species and protecting the other non-targets that we're trying to proliferate in these littoral zones. I probably missed other folks that have contributed to this, but these are the works that I'm familiar with that have contributed to our decisions to proceed with larger scale treatments and investigation of that. So we're talking about a herbicide treatment in Fish Lake. Fish Lake is a 250 acre or 228 acre lake in central Florida. It sits right between East Tehopekaliga and West Tehopekaliga. Pardon not having a comprehensive map to show, but I think it's understandable where we're talking about. This lake is an elliptical basin, so it has as you can see, a circumference of littoral edge, fairly extensive. Probably over 50% of this lake is littoral, but there's also a deep basin that's over 8 foot in depth. That is also a significant proportion of the total volume of that lake. The treatment was a 50-acre plot and a 228-acre lake, so a fairly significant treatment area on the southern littoral edge. The target concentration in the prescription was 48 parts per billion. And again, 50 acres with an average depth of 5 feet, so 5 PDUs per acre foot. This was treated with 2 airboats with trailing hoses, delivering herbicide at the surface on 20-foot swaths, and accomplished in about 3.5 hours, getting kind of detailed in the operation. But I did want to point out these are GPS recorded lines of the treatment. You can see the dexterity and the precision of the application, a highly refined treatment, well placed in the area that was designated. So a very high quality controlled treatment with good precision. On the day of treatment and several days after, there was a southeast wind pushing waves to the northwest, exactly opposite of where the treatment was applied. And we'll talk about that moving forward. To evaluate the performance and behavior of the fluoroxyphene benzyl and the acid, we conducted several survey techniques, standard techniques, and with hydroacoustics to monitor the biovolume of the submerged aquatic vegetation in the water column. Also point intercept surveys throughout the lake, these black points here, to estimate the abundance and frequency of species presence, largely dominated by Hydrilla, mind you. We also have water grab sampling from stations, these white dots, for analytical determinations of concentration at 24, 48, 72 hours after treatment, also 1 week, 2 weeks, and 5 weeks after treatment. So really solid, high-resolution, spatial, temporal evaluation of the herbicide treatment and the effects on the plants within the entire lake, inside the treated area and comprehensively outside of that as well. Hydroacoustic surveys, again, were performed with a fathometer with the Lowrance unit recording, GPS with the transducer also recording 20 kilohertz signal, sending and a 20-degree down scan. I'm getting technical here, but if you've used one of these devices, a very interesting tool that I'm becoming accustomed to and really drives my interest in geographical information systems analysis, spatial analysis. It's a fascinating tool that can collect high-quality data very efficiently on the water and fairly economically. But I won't get into details of this, but basically you should consider these raster heat maps as a proxy to the density of submerged aquatic vegetation in the water column. So let's have our dessert before we get into the salad. I'd just as soon start with showing you the efficacy and performance of the herbicide before we get into dissipation and non-target injury. Let's talk about what this herbicide did in the treatment. And so here we have just 1 week prior to the treatment. The average biovolume was 64% in the treated area and 63% in the non-treated area. Think of the littoral edge as the non-treated area. You'll also notice not a lot of submerged aquatic vegetation in the basin due to the depths and low light conditions. So we're really talking about a strong littoral occupation of SAV, which is almost exclusively Hydrilla. And so this is, we're right at the starting line here. Moving on, you can see at 35 days after treatment, herbicide effect taking, here's time 0. Here's 31 months later, you can see how the herbicide is performing. 26% in the treated plot, 44% in the non-treated. Let's move on into 2 months after. Then we're getting into 3 months. You can see how the herbicide has progressed nicely with suppression of SAV within the treated area and some of it outside of it, but mostly confined to within that treated area. And then peaking at 133 days, which is effectively 4 months after, 4 to 5 months after treatment, where the biovolume has reduced down to 4%, while it remains at 54% in the non-treated area. We'll also point out that the date of this time point is December 17th. We're also coming into the winter season. Florida has 4 seasons. They're obviously much more mild in Central Florida, but they do have an effect on plant performance. And so we're talking about the cooler period of the year, accentuating the results of suppression being measured within this treatment plot and outside of that. And then as we come into January, 160 days, February 2019, we're starting to see a little bit of recovery here. And then we get into April, again, some new recovery, and then the final day, 300 days after treatment, showing recovery from that herbicide treatment, significantly lower than the non-treated control, or not the control, the untreated area, sorry. So let's kind of review with Hydrilla suppression efficacy. Cooler temperatures during the winter months, extended suppression, where we're seeing strong effects, 30% reduction relative to the non-treated areas after 300 days of treatment. I think that's pretty substantial relative to our other options, including Endosol. So we're in the ballpark here. This is a highly effective treatment. It performed very well under these conditions. It was smart to treat late summer to take advantage of the winter months. Unfortunately, I'm not able to report past this timeline. We can assume that at this point it's probably due for another treatment. Let's just put it that way. Herbicides aren't meant to last forever. And so if you can buy 300 days of effective suppression, that generally comes out as a win, as a benefit in the economics. Again, 30% suppression measured 300 days after. Suppression was measurable 100 meters beyond the treatment area, which is basically up to the edge of that basin. So you have some dissipation of activity outside of the treatment plot, as expected. And the final note is the non-treated area actually increased in its growth. So we're talking about plant that was growing out, continuing to grow out during this time period. So again, accentuating the activity of the herbicide suppression. Moving on. So let's talk a little bit about dissipation of the fluoroperoxyfen benzyl and acid forms of the active ingredient. Again, reminding you of the stations where water samples were collected. Samples were collected at 6, 24, 48, and 72 hours after treatment, and then also 1, 2, and 5 weeks after treatment. So again, a really high resolution timeline of the events of herbicide movement and change, and then of course comprehensively covering the entire lake inside and outside of the treatment plot. Samples were analyzed for concentration for both the parent and acid, and then these concentrations values at the georeference stations were interpolated with a prigging technique so that we could look at the spatial distribution of the herbicide concentrations in the lake. So this is a very busy slide, so let me talk you through it here. It's also highly visual. So at the top you have the benzyl form, the parent active ingredient, and you can see a timeline from 0 to 864 hours, which is the same as 5 weeks. So this is in hours. So you got the parent material you can see is super hot at time 0. That's what an active treatment looks like. And then at 6 hours, you can see dramatic reductions of the active benzyl formula, FPB. And then 24 hours, 48, so you see a steady decay of the benzyl active ingredient. And that shows up here on this plot, the red line, which is treatment, basin, and non-treatment, red, yellow, and blue. Solid lines. So the treated area, you can see this exponential decay function that basically goes to extinction at approximately I think the 168-hour mark is when we pick up, no longer detect the parent benzyl formulation, FPB. And then what's interesting is as we see decay within the treated area, we see a small bump of that active ingredient in the basin, and then we do not pick up any of the benzyl within the non-treated littoral edge within that area. So that's what, this is a very tight area, and you can see how this graph is expanded out, because now we're going to talk about the acid profile over space and time. And here it tells a little bit of a different story, where we see no detectable acid at time 0, very small amounts at the 6-hour mark. Now it's starting to heat up 24 hours later in the treated area, and then continues on increasing 48 hours and peaking at 72 hours after treatment. So now you have what's called a biphasic trend of concentration, where it increases, and then after 72 hours it starts to decrease at 1 week, 2 weeks, and then 5 weeks where very low amounts are detectable, and it shows on this graph here. So you see this biphasic trend. You see a strong spike in the treated plot, again, the red indicating the treatment area, and then it equilibrates with the basin and also the non-treated. So they equilibrate at about the 200-hour mark, and then trend downwards towards extinction within 1 month of treatment. This is standard from what we understand with this herbicide, apparently, and so it was gratifying to see how the herbicide behaved the way it was supposed to, where the benzyl formulation is rapidly dissipated. Dissipation can be in multiple forms. Adsorption, where it actually adheres and is absorbed into the plant to be active. And we also have hydrolysis, where it converts to the acid. We've also seen that, where we have a lag in spike of the acid relative to the decay of the parent material. And then we also have diffusion, where the herbicide is moving outside of the treatment area into other areas. So all three forms have been observed with both the benzyl and the acid. And again, mentioned how the acid is biphasic, where it will increase relative to the amount of benzyl formula remaining, and then decreases as it starts to become metabolically broken down or hydrolytically broken down. It does have longer residency and higher mobility than the benzyl formula. So again, these are what we're observing with these trends. Dissipation is a result of movement and mass flow and hydrodynamics of the lakes. Let's talk a little bit about going back to the wind conditions. On the day of treatment and 2 days later, we had south-southeast winds pushing north at 4 to 6 miles an hour. You can see the arrows indicating the direction of the wind on the time of treatment, and then shifting southeast into northwest. Basically, the longest fetch you can achieve is along this longitudinal axis of the lake. So a really strong fetch on the lake, in spite of really moderate wind conditions, probably contributing to the movement of the herbicide out of that narrow treatment area, and then, of course, dumping into this very large basin of deep water, contributing to the dissipation effects that were modeled with the data collected from the water stations. Let's move on. So again, wrapping up with dissipation of FPB and FPA, acid hydrolysis was apparently very rapid. FPA was approximately or over 50% of the detectable quantity at 48 hours after treatment. As you can see here, this bar graph representing FPB in red and FPA in orange. We have 0 to 72 hours and then 1, 2, and 5 weeks after treatment. You can see at 48 hours, again, FPA is over half of the quantified detectable amounts. Acid concentration is biphasic. It increases and then decreases, and that's what we see. An increase in the acid up to 72 hours, and then starts to decrease slowly over the next several weeks. And then this is what would be characterized as a first-order kinetics reaction, and if I was interested in math, we would be able to calculate the constant value for the degradation rate of the parent material and also the degradation rate of the acid, and those two combined would dictate or tell you the projection of how long the acid form would remain in a water column based on those constant values. And of course, I've already described all the other factors that can contribute to that, so it's really a moving target in terms of the dissipation, but consistent with what we think we understand about this herbicide. I'd like to also suggest, too, that we think that probably quite a bit of it was absorbed into the plants. We talked about that KOW value, the lipophilic value, and its ability to bind to organic materials and lipids and fats. And so that's what plants are made of. And so when we look at the 48 and 72-hour mark, for instance, and the 1-week mark, we notice that, you know, besides the transition from the benzyl to acid formulation, we automatically have basically a loss in the mass balance of the total amount of herbicide that was applied and what's remaining within those time periods. And what we see here is between 48 and 72 hours, there's not a lot of movement in terms of loss of actual product. We see a shift from benzyl to acid, but right here, this is probably the time period. I'm speculating, of course, but this would, you know, I might suggest that the remainder is probably been acquired by the plant material. We're talking about treating topped out, heavy, dense hydrilla in the treated area by you, 60%, over 60% biovolume. And so my estimation is, unvetted, of course, is about 50% of the active ingredient was absorbed to the plant within the first 48 hours. After that, the remainder continued to dissipate by converting to acid, which becomes mobile and then moves out of the treated area, so on and so forth. We already mentioned FPA's degradation is slower than FPB, and then at 5 weeks, an estimated 18% of the total amount was still in the water. Again, there's errors of estimation here, but within reason, this is what we're picking up on. And then FPA, again, is also more mobile with time to detection corresponding to distance, which is this graph down here, where you can see at 0 hours, we see within the treated plot, acid picked up within 6 hours. I can be done in 2 minutes, if that's okay.
Okay, yeah.
Great. So anyways, distance from the treated area corresponds to when acids are detected, demonstrating movement due to hydrodynamics of the lake system. Talking about non-target impacts, we did see acute injury to the lilies and pads, which was expected, and they were outside of the treatment plots, which would suggest that there is activity with the acids. Valsinaria and Nufar Nufar did show some injury, but it was also recovered. It was observed to recover, and it also appeared to not be dependent on herbicide treatments, and so appeared to be fairly resilient. Valsinaria, interestingly, here you see a slight trend of movement of increase inversely proportional to decrease in hydrilla. So we know Valsinaria is rather tolerant of the fluoroperoxyfen benzyl, but it's highly sensitive to hydrilla competition. And so when you can reduce competition with the herbicide treatment, Valsinaria responded positively. I think that's mainly what we're talking about here. I think there's still a lot of work to be done on the non-target impacts to understand how we can tailor the treatments based on timing and rate control. This was this is the maximum label rate that you could apply in a very small lake system. I can talk about this, I think, really quickly. On the x-axis, we have abundance of hydrilla on a scale of 0 to 1. We have evenness, which is basically diversity, species diversity. And then we have biovolume. And so biovolume is strongly correlates strongly with the abundance of hydrilla, suggesting that when we're recording SAV with the acoustics, it's mostly going to be hydrilla. On this case, we see an increase in diversity, species diversity, at the lowest abundance levels of hydrilla, and then showing it decrease when hydrilla increases. Again, showing the competitive effects of hydrilla as opposed to the herbicidal effects. So controlling hydrilla can enhance the biodiversity and evenness of the community structure within the littoral zone of lake systems. So in conclusion, hydrilla suppression extended late spring 300 days. Valsinaria exhibited tolerance. Nufar symptoms are acute but temporary. Floating leaf species are acutely susceptible. FPA is highly mobile with longer residency than the FPB, and also reached equilibrium with throughout the lake. This is a small lake, though, and I think it's unique to Fish Lake. This would not be observed in larger lake systems like Lake Toho, which is 18,000 acres. Observed non-target injury outside the treated area with no apparent hydrilla suppression, suggesting the acid form has some activity on these highly sensitive floating leaf plants. And this creates opportunities for us to enhance the selectivity of the treatment with rate control and timing. Thank you all very much for your attention, and I hope I was able to share something that was new today. Thank you.
Certainly. Thank you very much, Dr. Leary. And so I'll give a quick minute for anybody to type in a question. You'll notice here I put a copy of our flyer advertising all of our summer topics. And next week we've got a mechanical harvesting presentation, once again by Dr. Leary, and then an aquatic weed control myths and misconceptions topic shared by Dr. Ben Sperry again. So if those catch your attention, we would love to have you back with us again at this time next week, and we'll send a separate calendar invitation for that meeting to get it on your schedule. And then you'll notice here the Dr. Leary's email and Dr. Sperry's email address, again, if you have questions. I have not seen any come in through the chat box, so we'll assume that questions are good for now. Dr. Sperry, we'll give you a first opportunity for any closing comments before we call it a day.
Sure. No, I appreciate it. Appreciate the opportunity, and that was a lot of fun. I look forward to talking again soon. Great.
We look forward to hearing more from you. And Dr. Leary, any final comments from you?
Yeah, no, I share Dr. Sperry's sentiments. It was a pleasurable experience. Kind of lonely here talking to myself, but I know there was a well-attended audience, and I really appreciate your attention. And again, Courtney, thanks for making the arrangements to offer this venue.
You bet, guys. We appreciate you sharing with us here in our platform. I did do a call check, and we had at least 83 on the line at one point during the call, so there was a lot of it just in the topic. And we're grateful. And we'll have it archived for future reference as well. All right, with that, guys, we'll call it a day and conclude our meeting. I hope you all have a good afternoon, and we'll look forward to learning with you again very soon.